Hello everyone, in today's lecture we will review the basic concepts of semaphores and go through a very typical semaphore example, the dining philosopher's problem. First, let's review the definition of semaphores. In operating system, two or more processes can cooperate by means of simple signals, such that a process can be forced to stop at a specific place until it has received a specific signal. For signaling, special variables called semaphores are used. A semaphore variable can be initialized to a non-negative integer value, and there are two operations, sem_wait operation for decrementing values and sem_signal operation for incrementing values. This pseudocode shows semaphores primitives. When sem_wait is called, variable s decrements 1. If s is smaller than 0, process is put in s.q. When sem_signal is called, variable s increments 1. If s is smaller or equal to 0, process is released from s.q. This is a simple example. Process A is in the processor already. Processes B, C, D, E are in ready queue. A sends sem_wait signal, turning s from 1 to 0. A can now pass through s.q and B enters the processor. Now B also sends sem_wait signal, turning s from 0 to -1. Hence, B is blocked in s.q. C enters the processor, and if C sends sem_signal, s will turn to 0. As a result, B is released from s.q, and process D enters the processor. Now let us do the dining philosopher's problem. This problem is introduced by Dijkstra in 1965. As the graph shows, 5 philosophers are sitting at a round table with plates of spaghetti. Forks are placed between each pair of adjacent philosophers. There are 5 forks in total. Philosophers can either do some thinking or eat. We are asked to design a discipline behavior or an algorithm that will allow philosophers to eat. This algorithm must satisfy mutual exclusion while avoiding deadlock and starvation. Note that a philosopher can only take the fork on their left or the one on their right, and they cannot start eating before getting 2 forks. Okay, we are asked to design an algorithm satisfying mutual exclusion and avoiding deadlock and starvation. Therefore, we should do some review about these concepts. There are 4 conditions for mutual exclusion, and that our design should satisfy. First condition is no 2 processes may be simultaneously inside their critical section. Second condition, no assumption may be made about speeds and number of CPUs, or we can say no assumptions are made about relative process speeds or number of processes. Third condition, no process outside critical section may block other processes. Fourth condition, no process would have to wait forever to enter its critical section. For the first condition, we should note that 1 fork can only be held by 1 philosopher at a time. After a philosopher finishes eating, he or she puts down both forks so that the forks become available to others. Forks in this problem are our critical sections, and the process remains inside its critical section for a finite time only. For the second condition, we should assume that no philosopher can know when others may want to eat or drink. Third and fourth conditions involve deadlock and starvation. Deadlock is a situation where 2 or multiple processes are waiting for each other to take actions. For example, in this graph, 2 cars are waiting for each other in front of a stop sign. In order to prevent them from waiting forever, some mechanism must be introduced. In this specific example, the car that's about to turn right has right of way and therefore go first. Deadlock can cause resource starvation because processes are all waiting for each other. Starvation may also happen when a process is denied access to a critical section. We will be discussing how to prevent deadlock and resource starvation in our detailed solution. Now we have our full design specification. We can start our design. One solution we can come up with is each philosopher first picks up the fork on the left, then the fork on the right. After the philosopher is finished eating, he puts down the fork on the right first. Why? because all philosophers start eating by picking up the fork on their left, putting down the fork on their right first can allow next person to use it. This increases efficiency, although I wouldn't recommend using other people's fork, especially during the pandemic. Our current solution is shown in pseudocode. We have a semaphore array consisting of 5 elements representing 5 forks. All elements are initialized to be 1. We have a function philosopher with 1 integer parameter. And inside the main function, we're calling philosopher functions randomly. For example, if philosopher 4 is called, while true, philosopher thinks. If the philosopher wants to eat, it triggers samWait on the 4th fork. This mod 5 here means we take the remainder of I plus 1 divided by 5. Therefore, samWait is sent to 0th fork. The philosopher then eats, and sam signal to 0th fork. If now philosopher 1 is called, he or she can access 0th fork. Philosopher 4 continues, sends sam signal to 4th fork, and finish eating. This solution, however, cannot prevent deadlock. If all philosophers are being called at the same time, they all pick up the fork on their left. Now all forks have value 0. When they continue sending samWait, all forks have value -1. Therefore, this is a deadlock, causing resource starvation. In order to solve this, we introduce our second solution. In our second solution, we set up a limit for the maximum number of philosophers in the room. Only 4 philosophers can enter the room at a time. Whoever finishes eating, exit the room. As you can see, another semaphore variable room is created and is initialized to be 4. This means the vacancy for this room is 4. Philosophers must send samWait to room before having access to forks. Now, if all philosopher functions are being called, they all send samWait to room. Philosophers 0, 1, 2, 3 comes in. Room becomes 0. The room variable becomes 0. Philosopher 4 sends samWait to room variable, turning it to -1. Therefore, philosopher 4 is blocked in the room queue. Next, philosophers 0, 1, 2, 3 send samWait to fork 0, 1, 2, 3, respectively, turning values of fork 0, 1, 2, 3 to 0. They then send samWait to fork 1, 2, 3, 4. These are forks to their right. However, only philosopher 3 gets fork 4. Other philosophers are blocked in corresponding fork queues. After philosopher 3 finishes eating, he or she returns 2 forks. Philosopher 2 is therefore released from fork 3 queue and gets fork 3, the 3rd fork. Philosopher 3 also sends sam signal to room while exiting the room, releasing philosopher 4 from the room queue. The moment philosopher 4 comes into the room, he or she sends samWait to fork 4, the left-hand fork, and fork 0, the right-hand fork. Philosopher 4 gets fork 4, the 4th fork, enters the 0th fork queue since the value of 0th fork is turned from 0 to -1, while fork 4, the 4th fork, is turned from 1 to 0. Assume that philosophers 0, 1, 2, 3 are not being called anymore. This process goes on until there is only philosopher 4 in the room. He or she can finally be released from the fork queue and gets fork 0. After philosopher 4 finishes eating, the room changes to its initialized state. Evidently, we have solved the deadlock and starvation problem. No process waits forever to enter the critical section. No process outside of critical section blocks other processes, and the selection of waiting processes into critical sections is not arbitrary. We have proved that no 2 processes can be in their critical section simultaneously. We can also prove philosopher functions can be randomly called. For example, here, any philosopher can still enter, and their orders don't matter. Therefore, this algorithm meets all conditions and satisfies design specifications. This is the end of the lecture. Thank you.